Welcome back, Astronomy 10, to your part 2 lecture for chapter 14. We're going to wrap up talking about galaxies and a few other things today. But before we begin our lecture in earnest, I want to pose a question to all of you, and if you need time to think about it, of course, you can just pause the video. But I want to ask you, does the universe look the same kind of in all directions? That is, does it appear homogeneous? And like I said, you can decide that for yourself. At this time, there's really no wrong answer. And we left off last time talking about galaxies and what they're made of. Stars and black holes and the dark matter problem. However, we did not talk about the cores of galaxies so much. Initial probing by radio astronomy found evidence of objects that give off a tremendous amount of energy in the radio band of the electromagnetic spectrum, seemingly without a visible component to accompany it. And as our technology and techniques improved, we found that the same objects were very faint, but also very blue, towards the high energy, far away from the radio portion of the electromagnetic spectrum. Very blue, very high energy. However, they only showed 2 absorption lines instead of all of the lines that a blue star would have, and they were all kind of slightly red-shifted. These were dubbed quasi-stellar radio sources, or quasars for short. Now I want to show you a few images of quasars, and those are, of course, in today's image bank. But I want to show you some pictures of quasars and active galaxy nuclei. And there are images in today's image bank. Some of them have the word quasar written on them, so you know that those are obviously quasars. But also there's one that has like 8 images in it with a bunch of sort of green overtones. And some of those are active galaxy nuclei, which are kind of the smaller cousins of quasars. So if we look at all of these images, do we kind of see any similarities? Especially the first 2 ones, the quasar images. We can see that there's like a bright area, right, that's like larger than a single pinpoint. There's material jets shooting out of them, right? There's kind of clouds of material outside, presumably, where the jets have shot a bunch of material outward. And so, yeah, we can see that there are indeed some visual similarities to some of these objects, right? And so we want to try to figure out what processes are actually causing these things to look the way they are, right? Causing these things to be in the state that they're in, to be how they are. So these objects, which are generally found, again, at the cores of galaxies, are roughly kind of like the size of our solar system, about 100 AUs or so across, sometimes bigger, sometimes smaller, of course. But, around that sort of order of magnitude, around that general scope. Now, because of that size, because they're that big, it's difficult to get a clear image of what they actually look like. If you remember, the speed of light is invariant in all frames of reference, and so the light from one side will reach us maybe hours or days before the light from the other side will, right? If this is like the close side, the light from the far side is going to have to take, it's going to have to go all the way through the object before it can, leave to get to us. To say nothing of the travel time, obviously, but just the time difference from one side of the galactic core to the other can be light hours or even light days. several light days, right? And so it's difficult to get kind of a clear image of what one of these objects really truly looks like. It's like if you're watching a football game, right, and you're watching a halftime show. If the band is all marching like in a nice tight formation, you can hear the song more easily. But if they're spread out all the way over the field, you're going to hear, you know, let's say you're sitting at the 50-yard line. You're going to hear the band that's close to you before you hear the band that's like way out near the end zones, right? And so it's going to kind of sound like the song is echoing or something like that, right? And for that reason, it's going to be more difficult to get an image of an object whose light, like will span several days. You can imagine trying to listen to a song that's like out of sync by several days. Now try to take an image, right? That the light is all out of sync by several days. It's hard to get an image, It's hard to try to get a clear picture of what's actually going on inside one of these objects for that reason. We say that essentially resolution is bad. Like the resolution on your monitor, on your phone screen, or something like that. Trying to resolve the individual details of that image is not easy, right? Also, the electromagnetic radiation around or coming from this object has a difficult time sometimes getting through the accretion disks around them. And that means that there are accretion disks around these objects. Now, accretion disks form around what kind of objects that we're familiar with? Obviously around stars that are forming, right? But what else? If you remember, there are accretion disks that kind of form around objects that are very bright in the X-ray portion of the electromagnetic spectrum, and those are black holes. Today we know that quasars are somewhere between like 10 to the power 12 and 10 to the power 15 solar luminosities. Very, very bright, right? 10 to the power 3 is 1,000. 10 to the power 6 is 1,000,000. 10 to the power 9 is 1,000,000,000. 10 to the power 12 is a trillion. 10 to the power 15 is a quadrillion. So you're talking about really, really bright objects. Granted, if they're bright in the X-ray portion of the electromagnetic spectrum, our eyes are not really so well attuned to that, right? So we can't see them so easily. We need like an X-ray detector. But in any case, quasars are very, very bright, and being the larger cousin of what we call AGN, or active galaxy nuclei, they're much brighter than active galaxy nuclei are. AGNs are generally something like 10,000 solar luminosities. This amount of energy coming from such a small volume can only mean one thing. And you probably guessed, yes, we're talking about supermassive black holes. Not just normal black holes, not like the ones left behind by massive stars, but these black holes that you would find at the core of a galaxy are sometimes between thousands to maybe billions of solar masses. They're very, very massive. Their gravity is so strong that their accretion disks are hyperdense, containing lots and lots of material. And because they're so hyperdense, if you wanted to compare the accretion disk around like a protostar, or maybe what's left around a white dwarf, if you scale that up to a black hole of about 100 billion or 100 million, or maybe all the way up to like 10 billion solar masses, in an orbit the size of Neptune's orbit around the sun, that's a quasar or an active galaxy nucleus, right? Now, as material gets pulled towards this black hole, around this AGN or this quasar or whatever you've got, conservation of energy dictates that the material in the accretion disk can heat up to something like 100,000 Kelvin, or several 100,000 Kelvin, in fact. And that's visible all the way up to, like, from the visible portion of the electromagnetic spectrum, excuse me, the visible part that we can see with our eyes, all the way up to, like, ultraviolet and even X-ray, right? Really very hot. So when something like 0.7% of the mass of a star gets transformed into energy via the proton-proton chain over the course of a star's life. If you want to compare that to the 15% of the mass in an accretion disk around an active galaxy nucleus or a quasar that becomes energy, so much so that tons of energy gets released via this funny process we call synchrotron radiation. Synchrotron radiation happens because you have a very strong magnetic field around, one of these very, very massive objects. You have lots of charged moving particles, and so you end up with a very strong magnetic field. And when a charged particle interacts with this magnetic field, sometimes it can kind of wrap itself around one of these magnetic field lines and just kind of spiral. And if it moves fast enough, this proton or this electron, this charged particle, can move fast enough to give off radio waves. And that essentially, you're taking tons of this matter, right? And this synchrotron radiation gives off tons of energy, right? This matter gets converted into energy, in an E equals mc squared kind of interaction. And the accretion disk loses about 15% of its mass to this synchrotron radiation that gets irradiated out into the universe. And the rest, of course, eventually, over the course of time, falls into the black hole, making it even more massive. This causes jets of radio energy to come out from its poles like a protostar, hence the quasi-stellar radio source or quasar nomenclature that we have for these objects. Now, in theory, if a galaxy actually has one of these supermassive black holes at its center, then stars should orbit it, right? It just makes sense. And thus, these stars should move very quickly, because they're a very massive object that has a very strong gravitational pull. And if that's true, then it should have very high red shifts as when it's going away, and very high blue shifts when it's coming towards us. And also, the center of a galaxy should be very bright. Indeed, the only difference between a bright supermassive black hole and a supermassive black hole that's not so bright is that an active galaxy nucleus is sort of being fed material as we're looking at it. And that, of course, accelerates and brightens. And for this to be so, the black holes must be generally between about 10 to 100,000, all the way up to about 5 to 10 billion solar masses. Most galaxies have supermassive black holes at their cores, according to our findings, and most of these cores have stars moving around them with high red and blue shifts that we can detect. Once upon a time, it was first noticed by someone named Vesto Slipher that galaxies that are very, very far away from us have red shifts, meaning they're moving away. And I don't just mean some of them, I mean all of them. So what could this possibly mean? Well, that could mean maybe one of two things, and that is maybe that we're standing still and everything is moving away from us because we are at the exact point where the Big Bang happened and we're at a special place in the universe. And that's crazy talk, right? That's geocentric thinking all over again. First we go from the Earth being at the center of the universe to the Milky Way being at the center of the universe. The other possibility, the one that makes more sense, and the one that has stood up to all of our vigorous testing, right? Every time we look out into the universe, we see evidence of it everywhere. The other possibility, the sane and sound one, is that the universe is expanding. Consider, if you will, a loaf of bread, okay? Let's say that you're baking a loaf of raisin bread. This loaf of bread starts out about this small, and over the course of time it blows up to a loaf of bread size, right? Now, if you want to consider the distances in between the raisins in this loaf of bread, if you were to try to take the perspective of one of these raisins into account, and you looked at all of the other raisins, it would look like all of the other raisins are moving away from you, because indeed they are. Because the loaf of bread is expanding, right? Thus, if every raisin moves away from every other raisin in the universe, or every galaxy moves away from every other galaxy in the universe, with a few notable exceptions, then the universe must be expanding. Now, like I said, there are a few exceptions. There are clusters of galaxies that are gravitationally bound, and those are only going to come closer as gravity brings them together. But if we look at one cluster compared to another cluster compared to another cluster, they're all moving away from each other, because the universe is expanding. Now, this next part is colossal. Edwin Hubble compared the distances to galaxies using things like standard candles, type 1a supernova, Cepheid variable stars. And what he noticed is this very interesting phenomenon that galaxies that are farther away have greater redshifts, or are moving away faster. This is called Hubble's law. And this is our greatest piece of evidence for the expanding universe. Obviously, if you were to look at two raisins at the very far end of a loaf of baking raisin bread, it would look like they were moving away faster, right? The farther away galaxies and galaxy clusters are, the more redshifted they are from our perspective, because the universe as a whole is expanding. And so galaxies that are farther away are going to be moving away from us faster, right? Or we're also moving away from them. But relative to us, relative to our frame of reference, our galactic frame of reference, if you will, galaxies that are farther away are moving away faster, relatively speaking. Now, what did we use for standard candles? What did Edwin Hubble use for standard candles when he was figuring this out? Oh, and by the way, Edwin Hubble put together this data. He was a very clever human being. He put together this data with very limited technology. And it turns out that he was right. He was off by just a tiny bit from our current measurements. We've been able to see galaxies and galaxy clusters that are much, much farther away than what he was able to see with his telescopes, right? Nowadays we can see much farther. And I think the number that he came up with was something like 70 kilometers per second per megaparsec, or something like that. And the number that he came up with is something like 71. So he was really close. It's maybe a couple percent off. 1.5% off, something like that. 1.3, 1.4. So he was really close. But we've refined the measurement from his original data with a greater sample size and greater depth of field, looking at stars, or excuse me, galaxies and galaxy clusters that are much, much farther away. But he was still right on the money. In any case, in order to make these measurements, what types of standard candles did he use? Well, obviously he used type 1a supernova. Those are some of the brightest objects in the universe, some of the brightest events, if you want to think of it that way, in the universe. And because they all happen at the same mass, right, this 1.4 solar masses, when a white dwarf comes up over 1.4 solar masses, they explode in this fantastic, brilliant event, a very short-lived event. But because they all happen at the same mass limit, they all have the same brightness. So they make a good standard candle, right? Just like, for galaxies that are close by, we can use variable stars. That's easier. But unlike type 2 supernovae, which can vary in brightness because they vary in mass, right? Different stars have different masses. And so when like a class O star goes supernova, it's going to have a different brightness from, say, a class B star. But type 1a supernova are not limited in that regard. They all have the same brightness. And so because we can identify their spectral signature, we can also use them as standard candles. So they're handy like that. But if we measure the brightness of these objects and correlate them to their distances and their redshifts, we have using this technique, we've built up this evidence for Hubble's law over the last, 100 years or so. Now, essentially, what this means is we've kind of built a distance ladder. For things that are really, really close, we can just kind of send like a radar ping, like the moon. We know exactly how far it is at any given time because there's a mirror on the surface of the moon. You can shine a laser at it, and it'll reflect the light, and if you have a good detector, at that distance, you're talking about 350 to 400,000 kilometers, so round trip, it's like 700 to 800,000 kilometers, right? And even if you have a really tightly collimated laser beam, it's going to expand a bunch. And so you need a detector that can detect that kind of spread out laser signal. But, if you can detect your own signal, you can figure out exactly what the lag time is, and you have a very accurate measurement for the distance from here to an object like the moon. And you can do that with, lots of objects in our solar system using like radio waves, right? That's not so hard. For stars that are kind of nearby, we can use parallax, right? Things that are, a few parsecs away, maybe a few dozen parsecs, maybe a few hundred parsecs, up to maybe like a few thousand at most. But in that regime, up to about maybe 1,000,000 parsecs, looking at especially stars in our own galaxy, and maybe some stars in like nearby galaxies, we can look at what we call spectroscopic parallax, right? If we can look at the spectral signature of an individual main sequence star, we can figure out, by its absorption lines and where the peak emission is, what the spectral class of the star is, and therefore how bright it should be, right? What's its intrinsic brightness or absolute magnitude is. Excuse me. And if we can compare that to how bright the star appears, what we call its apparent magnitude, we can get a sense of how far it is, right? For objects that are a little further, we can use, for like nearby galaxies, we can use RR Lyrae and Cepheid variable stars because there's this relationship in between the period of pulsation, right, a period of variability, and the brightness or the luminosity of the star. And so using those two pieces of information, we can discern how bright the star actually is intrinsically and compare that to how bright it appears and get a good sense of the distance to that object, right? Makes a nice standard candle. And for distant galaxies, things that are like, a billion light years away or whatever, we can use things like type 1a supernova, all the way out to essentially the edge of the visible universe, as far as we can possibly see since time has began. And so we can basically measure the distance to just about any object in the universe that we can see using this distance ladder. Now, if we wanted to plot out the redshift of these distant objects versus our distance to them, the Hubble constant is the slope of the line for all of these redshifts for distant objects. And so essentially we have like a map for space-time and essentially all of the visible universe. And because we've been able to map out space-time and the visible universe kind of in all directions, there's, I think it's maybe the last image in today's bank. Let me check. Yeah, it's the last image in today's bank. If you look at the last image in today's bank, you can kind of see that, well, let me help decode this image for you. In the middle, there's like a bulge and then there's like a flat disk, right? That's the Milky Way, and we can't really see visible light through that because of all the gas and dust and stuff that make up the Milky Way, right? All of that gas where there's star formation going on in the spiral arms. Light doesn't go through that so well, right? Just like there's tons of gas and dust sort of in the central bulge, right? In the galactic core. And so we can't see lots of stars and galaxies there, right? However, pretty much everywhere else in the sky that we look, we can see that there are tons of stars and galaxy clusters in pretty much every direction. Now I know what you're used to looking up at the sky and seeing with your naked eye, because your eye is not, some infinitely powerful telescope or whatever that can see kind of out to the edge of the universe. What you're used to seeing is a few stars and lots of blank sky. But this map is actually a map of what the sky really looks like at greater distances, right? And if you look at the numbers that are next to these objects, like if you look at the very bottom, what's that say? It's the Sculptor supercluster, 0.054, that is the distance in megaparsecs. Or, remember, a parsec is 3.26 light years, a megaparsec is 3.26 million light years, or 3,260,000 light years. So M31 is 1 megaparsec from us. This Sculptor supercluster is 0.054 million parsecs. The Pavo Indus supercluster is 0.015 million parsecs from us, and so on. If you look kind of in the lower right, there's this thing that says Norma and the Great Attractor. The Great Attractor is this thing we're not really quite sure what it is, but it's slowing down the expansion of the universe in that area, in the area near it. So we think it's probably, some really super crazy, great, big black hole or something. If you look kind of at the top, just to the right of the top, it says the Virgo cluster, 16 megaparsecs. And the Virgo supercluster is actually the cluster that we're kind of a member of, and the center of that is about 16 million parsecs from us. Now, we're going to pretend that we're colorblind here for just a second, right? And if you don't see, the reds and greens and blues and purples and all that, which are, the sky doesn't actually look like that. Those are just color-coded, so we can kind of see where these clusters are, in what parts of the sky. And if you take the color out, Does, if we look at, large scale, does the universe kind of appear the same, kind of in all directions? Does it, as we asked at the beginning of class today, does it appear homogeneous? I'll, of course, let you answer that for yourselves, but obviously, the farther back, you look, this is only like kind of the first layer, right? There's obviously more galaxies and galaxy clusters behind those, going all the way out to the edge of the universe. Okay, I hope you've enjoyed today's lecture as much as I've enjoyed giving it. That's all for today. Please get a hold of me if you have any questions, and I'll see you next time.